Nuclear energy is a powerful force. It can light up our cities and power our industries, but it also comes with risks. One of the biggest risks is radioactivity. Radioactivity is a type of energy that comes from certain atoms. These atoms are unstable and they release energy to become more stable. This energy is what we call radiation. Radiation can be harmful to humans. It can damage our cells and lead to health problems. That's why it's so important to monitor radioactivity in nuclear facilities. We need to make sure that workers and the public are protected from radiation exposure. This is where radioactivity monitoring comes in. Radioactivity is invisible. We can't see it, smell it, or taste it, but it's all around us. Small amounts of radiation exist naturally in our environment, but nuclear facilities contain higher levels of man-made radioactive materials. These materials can release tiny particles into the air. These particles are called airborne particulate radioactivity, or APR. APR can be dangerous if it's inhaled. That's why it's crucial to monitor APR levels in nuclear facilities. We need to keep the air clean and safe for workers to breathe. Continuous air monitors, or CAMs, are essential tools for monitoring APR. They are like smoke detectors for radioactivity. They constantly sample the air and measure the amount of APR present. CAMs are placed in strategic locations throughout nuclear facilities, especially in areas where APR levels might be higher. These might include areas near radioactive materials or where maintenance work is being done. When a CAM detects a high level of APR, it sets off an alarm. This alarm warns workers to take precautions, such as putting on respiratory protection or evacuating the area. Placing CAMs in the correct locations is vital for accurate APR monitoring. If a CAM is not positioned properly, it may not detect a dangerous APR release. Imagine a CAM placed too far away from a work area where radioactive material is being handled. The CAM might not pick up on a spike in APR, putting workers at risk. That's why scientists and engineers have developed methods for validating CAM placement. They want to be certain that the CAMs are in the optimal spots to detect any potential APR hazards. Section 5. The Science of Validation, KDE Plots and Correlation. One method of validating CAM placement involves using something called KDE plots. KDE stands for kernel density estimation. It's a statistical way to visualize the distribution of data. In this case, the data points represent APR readings from the CAMs. By plotting these readings on a KDE plot, scientists can see how the APR levels are distributed over time. Another important tool is correlation analysis. This method looks for relationships between different sets of data. For example, scientists might compare APR readings from a CAM near a work area to readings from a CAM near a ventilation system. If the readings are highly correlated, it means they are closely related, and this helps confirm that the CAMs are effectively monitoring the flow of APR in the facility. Section 6. A case for safety CAMs in action. Let's consider a real-world example of how CAM placement validation works. Imagine a team of workers is tasked with replacing a component in a nuclear reactor. This component has been exposed to radiation for many years, so there's a risk that it might release airborne radioactive particles during the replacement process. To ensure the workers' safety, CAMs are strategically placed near the work area and near the ventilation system. As the workers carefully remove the component, the CAMs continuously monitor the airborne radioactive particles levels. The readings from the CAMs are compared and analyzed using KDE plots and correlation analysis. The results show a strong correlation between the two CAMs, indicating that they are accurately tracking the airborne radioactive particles released during the component replacement. This gives the workers and safety personnel confidence that the CAM system is working properly to protect them. Section 7. Breathing easy respiratory protection for nuclear workers. When airborne radioactive particles levels exceed safe limits, respiratory protection becomes crucial for worker safety. This protective gear acts as a barrier between the worker's lungs and the contaminated air. Respirators range from simple face masks to more sophisticated devices that supply clean air from an external source. The type of respirator required depends on the concentration of airborne radioactive particles present. Accurate airborne radioactive particles monitoring by CAMs is essential for determining the appropriate level of respiratory protection. If a CAM detects a sudden spike in airborne radioactive particles, it might trigger an alarm, signaling workers to don their respirators immediately. Section 8. The future of nuclear safety: continuous improvement. The field of radioactivity monitoring is constantly evolving. Scientists and engineers are always looking for new and better ways to protect workers and the public from radiation exposure. One area of focus is the development of more sensitive and reliable CAMs. These advanced CAMs will be able to detect even lower levels of airborne radioactive particles, providing an even earlier warning of potential hazards. Another area of research is the use of artificial intelligence in radioactivity monitoring. AI algorithms can analyze massive amounts of data from CAMs and other sensors to identify patterns and predict potential problems before they occur. Section 9. Nuclear energy: a clean energy future. Nuclear energy has the potential to be a major source of clean energy. Unlike fossil fuels, nuclear power plants don't produce greenhouse gases that contribute to climate change. However, the safe operation of nuclear facilities is paramount. Robust radioactivity monitoring systems, like those using CAMs, are essential for protecting workers, the public, and the environment. By investing in advanced monitoring technologies and rigorous safety protocols, we can harness the power of the atom while minimizing the risks associated with radioactivity. The future of clean energy may well depend on it.